Hi, welcome to what are going to be a few video lessons on mathematical induction. And we're going to start off really slow just to sort of get used to the idea of what exactly is going on when we're doing mathematical induction. And keep in mind that these videos that I'm going to do for you here are not actually supposed to be replacements for what the textbook does. These are just supposed to help you in addition to what you'll find in the readings, to help sort of conceptualize this. And what I'm going to try to do is present this to you first in a more intuitive way so that when you do go read the text, or if you've already read the text and you're not sort of quite getting a grip on what exactly they're trying to say, that this will be helpful to you. So again, this isn't going to be in any way a replacement for what's being done in the text, but this is supposed to be complementary to that. So that said, if you already have a good grip on mathematical induction, then you should feel free to skip these. But if you've never come across mathematical induction before, this is a really good place, I think, to start. So I'm going to use an analogy first to talk a little bit about mathematical induction. And actually, the first thing I should point is that mathematical induction is not a kind of inductive reasoning. So let me just flag this here, and I'll say that this is not inductive reasoning. So don't confuse the two together. So this is not inductive reasoning in the way that you see it in science, right? So make sure to keep that distinct. So I'm going to give you an analogy that I think helps to get a feel for what mathematical induction is. And this is what we call the domino analogy. And the analogy works like this. Suppose you have a bunch of dominoes, and you can set them up. I can actually make that line a little bit thicker here. I'll use this guy. So suppose you had a bunch of dominoes that were all stood up like this. And you want to convince your friend that, look, each of the dominoes has a particular kind of property. Namely, when pressed, they'll fall over, right? So if you were to push one, if I were to push this one, it'll actually fall over. It won't stay stable. And in fact, given the way that I've set these guys up, if I press on this first one, that one will fall over and knock the second one down, and the second one will then knock the third one down, and the third one the fourth one. And there's one way I can explain this to my friend by going through every single one of these dominoes. And I can say, look, if I press on this first one, that'll knock this guy down. If I press on this one, I'll knock that guy down. If I press on this one, that'll knock that guy down. And then when that guy starts falling over, that'll knock this guy down. And at the end, what I'll have is all of these dominoes having fallen down. But the problem, so that reasoning, I think, is perfectly good when we have just a finite number of dominoes. But suppose we had dominoes that went on forever, and they were all lined up like this, right? So I've got an infinite series of dominoes that have a starting point, but they go on forever. If I use the same kind of reasoning for my friend, I'll never be done, right? Suppose I get to the 1000th domino, and I say, look, if the 1000th domino falls over, and you have the next domino there, the 1001st domino, then clearly it'll knock that one over as well. And I have to keep going, right? I mean, I can't ever get to the end of the whole series because the series is infinitely long. So what mathematical induction lets you do is say something about all of these dominoes, the infinitely long chain of dominoes that we might have set up. And the reasoning kind of works like this. Rather than telling my friend, look, if this one in particular falls over, then it'll knock the next one over. What I can say instead is, look, suppose I'm anywhere down in the series, right? So I see the line of dominoes at some arbitrary point. And then I say, okay, given that this one or sorry, not this one in particular, right? That's not the way I should do it, but give me any point in the series, right? So suppose I'm at this big long window and what I see, let me actually just clear this out right here. You can't, I'm somewhere down in the series, so I'm not quite sure what I've seen on the left-hand side, but I know I see two dominoes right here, and then this sort of goes on to the right, and I never see where it ends either. I can say the following to my friend. Suppose this arbitrary domino right here, right? I don't know exactly where it is in the sequence. I just know that I have some arbitrary domino right here. And if this one falls over, right? So if this one has the property of having been pushed over, has been falling over, then clearly the second one will fall over as well because this one will press onto that domino and push it one over. So the way I'm doing this explanation to my friend is saying, look, all I know is that this arbitrary domino that I'm looking at, that this one, I'm assuming this one is falling over. And under that assumption, I can say something about the next one in the series, namely that it will fall over as well. And because I'm not saying anything in particular about this one, right? So if you can imagine that these are all numbered, right? This is maybe number 1, this is number 2, this is domino 3, this is domino 4, this is domino 5, on up the series. The reasoning I just used wasn't about a particular domino, right? I might have said, look, just let it be some domino. Let me give it a number k. Okay, so, and the one before that would have been k plus 1, or sorry, k minus 1, and back. And I'm not quite sure what number specifically this domino has. I just know the number of this domino is k. The one before it is k minus 1, and the number afterward is k plus 1. And then this would be k plus 2, and on it goes, infinitely long. The reasoning that I'm using is I'm saying, look, suppose k is falling over, right, or has fallen over, if you like. Then I can tell you something about the domino next to him, right afterwards in the sequence, namely domino k plus 1, which is it will also have the property of having fallen over. Why? Well, because look how close they are to one another, and if this one falls over, before it's finished falling over, it'll start pressing on the domino after it, which will cause that domino to fall over as well. So I'm basically reasoning from this arbitrary case k, and saying something about what will happen to case k plus 1, to domino k plus 1. And by doing that, I can say something about all of the dominoes that are lined up in a series like this. I can say, look, if I press the first one, right, so I have to press the first one over. So if I press the first one, then the next domino will fall over as well. So I establish that. And then I say, and for any domino k, if k was pressed or has fallen over, then k plus 1 has fallen over. Then I can conclude that all of the dominoes have fallen over. In other words, what I've done is I've said something about the very first case, case 1. I've said something about this first case, right? That it will fall over, or it has fallen over, if you like. And I'm being a little bit loose here, and we'll make this a little bit more rigorous, but this is just to sort of get you into the right kind of headspace. So I say that, the first domino has fallen over, right? So this is my very first one, the base case, if you like. So I say, look, in the first domino, which I will just call the base case, I show that it has fallen over, right? So I need to argue that it's going to fall over. And then I use this other kind of reasoning. I say, look, if case k has fallen over, then domino, or case k plus 1, has fallen over as well. By establishing that claim, I've made a claim about all of the dominoes. This second step here, right, so if I say, if k has fallen over, then k plus 1 has fallen over, this is called the inductive case. Inductive case. And what I have to do here is, you'll notice that I've made an assumption about k, right? I'm saying, look, suppose k has fallen over. Then I can say that k plus 1 has fallen over as well. So I'm making an assumption about k, and then I'm saying that something follows about k plus 1, right? That's what I need to, that's the reasoning that I'm using to establish. So that's what we call the inductive case, right? So you assume, the inductive case, is that if it holds for k, then it holds for k plus 1. And what's called the inductive hypothesis, it's a little messy, but you'll get the idea. This is the inductive hypothesis. The inductive hypothesis is just the hypothesis that the antecedent is in fact true, right? So I say, assume that k in fact has fallen over, and then I'm going to argue that the next domino beside it has fallen over as well. So the inductive hypothesis is that k, right, the antecedent of the conditional, is in fact the case, that it does in fact have the property. So let me just end on that note. So this is, I think, going to be an intuitive kind of analogy here to help keep in mind of what's going on in mathematical induction. And one of the important things to keep in mind is that you have this series, right? That all of these dominoes are lined up in just the right way, so that we can actually say something about all of them in that series. So hopefully that analogy will be helpful to you, and in the next video we'll do something a little bit more rigorous and go over an example of how mathematical induction is actually used in mathematics and in our case in sentential logic.